So these talks are posted. This picture is not for here. I'm not really that vain. It's for people who view the talks online. But if you want the slides, they're on xaprb.com, my personal website. And you can tweet me and you can email me, and I like both of those. Don't LinkedIn me. That's going away soon. All right. So what this talk is about what happens as systems get bigger and the workload gets heavier. And I think we all kind of intuitively know what happens, that they often get really twitchy and weird, and unpredictable kinds of things happen. And this talk is about how to form a mental model of what's really going on there. And there's some math, and then after we talk about the math, we're going to throw away the math, because the math is just there to kind of build the intuition of what's really going on in the systems. And then I'm going to tie this into a couple of other things, and hopefully you can walk away from here with just some really simple takeaways. So a couple of the things that we're going to cover during this talk is, what is a system's operating domain? And I'm going to tie this into some other people's work. The next thing is, how can we define load? Like, we talk about systems under high load, so what does that actually mean? And load limit, like, we all want to know, how close am I to the limit of the load that my systems can do? So what is that load limit? How can we see it coming? That's the part where we start to say it depends. And can we measure that? Can we model it? And how does the system behave as it approaches that limit? Okay. So let's start with the operating domain. And the operating domain is this region, sort of a mental model with a couple of different dimensions within which our system operates. And conceptually, it's basically like the iron triangle of good, fast, and cheap. But I'm going to tie this into Jens Rasmussen's model of that he drew for talking about how systems operating domain is bounded by safety on one side. And the operating state is where the system is kind of conceptually at the moment, and it bounces around a lot. So I'm going to zoom this picture in a little bit bigger, and I've got a link to the paper from which this was drawn at the end, so you can read this, which I encourage. So in the middle, we've got this region, which is kind of like the region in the middle of the iron triangle of good, fast, and cheap. He's defined it particularly in terms of thinking about what happens on the left-hand side here, where we approach the safety boundary. And there's this space of possibilities in the middle. That's the white space where our system can kind of bounce around in response to changing circumstances and pressures. And there's a few forces at work on it. So from the top on the right, sorry, I'm doing this in mirror image here. So from the top on the right, we have the boundary of economic failure. If the system crosses that boundary, we go out of business, right? We hard crash. On the bottom right, we have the boundary of unacceptable workload, which is, and by the way, he's thinking about systems in terms of like humans, like working in an operating room and things like that too. And the analogy here would be, if people stay awake too long, they literally fall asleep on their feet, right? So if you cross that boundary, then you crash again. And then on the right-hand side, we've got the safety boundary, and if you go past that, you have an accident and something really bad happens. So this space in the middle is where we keep our systems operating through various kinds of things. And occasionally, we cross one of the boundaries, and then something bad happens, and we react. One important thing to note is that the forces that he's considering mostly in drawing this model, which is why there's two lines on the right-hand side, is the forces that are away from like economic and workload constraints and towards the safety constraints. And so he's got two lines drawn on the right there. There's the one where we actually set the safety boundary, like the speed limit or other kinds of policies. And then beyond that is the actual accident boundary. And we don't know where that is. That's a really important point. So we know where the speed limit is, but we don't know how fast we can go before we actually crash the car. We only know that when we crash the car. And so this system operating point kind of bounces around. It's always moving in response to, various changes, policies, whatever. And then we have an accident and we go, ooh, that was the real speed limit. Let's set the speed limit at 55 to keep people away from the real speed limit. But we don't know where that is. We only know where we set that arbitrary boundary. So I'm going to extend this model a little bit. And I'm going to claim that there's actually, the boundaries on all sides are unknown. So the real boundaries on all sides are the red lines, and we cannot cross them. If we do, something really bad happens, but we don't know where they are. So we draw these boundaries inside. So we have policies on finance, make sure that you keep at least $10,000 in the bank account so that you don't have an overdraft. Or, if the servers are starting to get pretty busy, then let's provision some more. That one looks like, CPU 90%. We need to have some free CPU. And so we kind of conceptually think that we know how far away to stay from these boundaries. And then we draw those limits where we think it's safe. And those margins are sort of the, don't go here because it might be scary kind of a region. So we got the margin of error on the left, that's the safety limit. We've got overdraft protection, maybe we actually literally have that in our bank account. And we've got over provisioning on the bottom. And what happens in that buffer zone is not clean. It's not linear, it's very fuzzy. And as we start to encroach upon it, we start to get warning signs like, ooh, maybe the wheels are rattling a little bit. Maybe I should take my foot off the gas pedal, kind of a thing. And so what we think usually is that we're going to get some kind of a gradually escalating, like, sort of like we do with our kids. If you have kids, if you say that one more time, all right, now I'm going to count to 3, kind of a thing. We think we're going to get sort of warning signs from our systems, but what usually happens is that they suddenly erupt. And this is especially true, I think, in the case where we start to get our systems heavily loaded. So the other point to note about this operating domain is that our systems always run in degraded mode, partially degraded. And what keeps the wheels on and keeps things working is the humans operating within the system. Humans are part of the system. And the humans are adaptive and clever and intelligent and have domain knowledge that is not built into the system itself and all kinds of different things. And they adapt and keep things going when the system itself wouldn't operate on its own. And Richard Cook has this, How Complex Systems Fail, which is another thing that I love to read every now and then. And he's got 18 precepts, and I'm just copying sort of snippets from number 4 and 5. Complex systems, almost by definition, have these changing mixes of failures in them, and we're always sort of going, ooh, that's starting to get dangerous, and I'm going to compensate for it. And they're always running in partially degraded mode as a result of that. So another way of saying this is that systems can and do function beyond their load limits, which is a sort of weird thing to say, but it's actually true. So with that in mind, let's talk about load. So we're going to talk about what load is and a good model of load that we can use to kind of move this discussion to the next level. So definition of load. There is no the definition of load. There are many definitions of load, and none of them is wrong, but there's one that's particularly useful for this discussion because it's going to tie into some things that will come next. And so my definition of load for the purposes of this talk is the sum of residence times, what you might think of as latency. It's basically while jobs are being processed, while work is being done. If you sum up all of that time during an interval and then divide it by the length of the interval, you get average concurrency during that interval. And I'm going to claim later that concurrency, especially average concurrency over an interval of time, is equivalent to load. And then that's the right definition of load for this discussion. Okay, so first equation, if we have a drinking game, drink now. There's going to be a few more equations. Just blur your eyes, let the equations go. It's useful to have the equations to kind of understand how this gets built up piece by piece, but you don't need to remember them or even really understand them. Just watch me put additional pieces on. Okay? So one possible definition of load that I'm going to take a slight tangent into for a moment, just to explain why it doesn't really work very well, is utilization. So load is related to, let's say it's correlated with utilization and queue length, but it's not the same thing. And it's a bit of a pity, but actually kind of a blessing in disguise, because utilization turns out not to be the right way to really practically measure and model our systems. So I'm going to go through some slides kind of really quickly because it's there for sort of reference material if you want to look back on it later. So I'll put my mouth into fast mode now. So concurrency that I talked about as being load is related to it is the number of requests in process simultaneously, and it's related to utilization. If you increase concurrency, you're going to increase utilization. And then we've got this average concurrency, which is, concurrency is instantaneous, and then if you average over a period of time, you get average concurrency during that duration. And utilization is different. Utilization is the fraction of time that things were busy, that the system was busy. And busyness is binary. The system is either doing something or it's idle. And utilization is just the amount of time, the total amount of time in observation interval t, subtract out the idle time, and then you get a percentage or fraction of utilization. And then the queue length, which is also related to utilization and load and so forth, is the number of things that are, it's either instantaneous or time average, just like concurrency. It's the number of things that are waiting in line to get serviced. Okay, actually, I think I'm just going to skip over that slide completely, and it can be there for your reference if you want later. So let's talk about the load limit in terms of utilization and why that doesn't really work very well. It would be, in some ways, it would be nice if it did work that well because utilization has a hard limit, 0 to 1. There's a very clear, like, if you want to know where your load limit is, it's at utilization 1. But that doesn't actually tend to work because load goes from 0 to infinity. And utilization only goes from 0 to 1 and doesn't tell you what happens after you get to utilization 1, which is things back up in the queue. So load can continue to increase if your system is overloaded. And utilization doesn't give you any way to know that your system is overloaded. It only tells you it's fully loaded now. Okay? And then the other thing is that the formulas and equations and all of these kinds of things and the familiar hockey stick curve and the knee in the curve and all that kind of stuff are super unintuitive, and the math is super hard, and you can't really measure the things that you need to use the model, and it ends up just being a waste of time. So you can trust me on that if you wish, because I've spent a bunch of my life chasing that and then realizing, alas, this is never really going to work in the real world, which is what most people who've studied queuing theory and everything find, that it only works in very specific circumstances. But what we can do instead is we can take this definition of load being concurrency and we can take it into a different domain. And this actually does lead somewhere good. So we will take it into the domain of scalability, and when we come out of that, we'll have a model that we can tie back into the operating domain model. So let's start with the definition of scalability because we need a clear definition to tie into a model. And in the end, we're going to be able to measure how our systems are working. And after that, you'll actually won't have to use the measurements and the model, but just this is a good motivation for understanding how it all fits together. So there is a model that I've used successfully for many years of scalability as a function of concurrency. And it's like literally a mathematical function. It's practical, it's easy to use, and it does match the domain really well. And here I'm going to start, so get out your shot glasses again, because I'm going to start with more equations. But don't sweat the math. So I'm going to illustrate how scalability works and how to build up this equation in terms of a kind of generic parallel processing system that takes a task and then subdivides it so it can do it faster. And when it subdivides it, it does those things in parallel, which creates concurrency, and that's where the speed up comes from. Okay, so we start with the simplest case. The ideal is a clustered system that can do some number of tasks per second with no parallelism, and then we add parallelism into it. Okay, and we add parallelism by subdividing the tasks and doing them concurrently so they can complete faster. And what that means is that since we're completing them faster, we can also complete more per unit of time, and that means increased throughput. So a couple of units have just popped up on this slide. Tasks per second is throughput, and that's a universal definition that you'll see everywhere. Completion over amount of time. And throughput is a function of concurrency. And that's an important point that'll also, you'll see that expressed in the equations that we build. So linear scaling literally is a straight line on a graph with concurrency on one axis and throughput on the other. And as I just said, concurrency is the independent variable. You know, there's a function, and throughput is the function of concurrency. So throughput goes on the y-axis, right? And ideally, we want that to be a straight line in our linear scaling system. That's the definition of linear scaling. Another way to say this is to express that the system's output is a linear function of load. So as you double the load, throughput or the work getting done doubles as well. So you're getting equal return on investment, if you will. So the equation that describes this is the first of, drink, is the first of several that I'm going to compose. And the Greek letter lambda on the top is just the slope of the line. It's just a function of how efficient the system is. And everything else is just linear. So it's just, if you take that out, then you basically just have throughput of n is x of n, lambda times n. So x is throughput. This is the x from Little's law. If you're familiar with Little's law, it uses x to denote throughput and n to denote concurrency and r to denote residence time. So I'm using those variable letters consistently throughout this talk. And again, note that the independent parameter here is n, concurrency. It's the driver. But alas, our cluster is not perfect. And really, which cluster is perfect, right? Linear scaling would come if we could completely, perfectly, and totally subdivide our tasks and execute them completely in parallel. But we can't because our cluster has some startup and some parallelism and then some finishing. So it's like scatter-gather. First you have to scatter, and that's usually linear, serialized, and then the scattered parts all run in parallel, and then you gather the results back together, which is, again, usually serialized. So what happens is it gets somewhat faster, but there's that serialized portion that can't get subdivided and parallelized. And Amdahl's law describes how this happens and what happens to the line as you add in a serialized portion. So I've added something on the bottom of the equation, which is this sigma component. And sigma is literally just the fraction of work that can't be parallelized. So if our little diagram had 5% of startup and completion stuff that had to be serial, then sigma would be 5%. And what happens is instead of following that nice linear line, we start to kind of degrade and roll off just a little bit. So Amdahl's law has an asymptote. And that parallelism still works, as you start to increase concurrency. But what it does is it just takes the parallel portion, and as parallelism goes, or concurrency goes to infinity during that portion, then that stuff effectively reduces to instantaneous. And what you're left with is the serial portion. And so the asymptote is 1 over the serial portion of speed up. So if 5% of our task is parallelized, then we can never speed up more than 20-fold effectively. Okay. So what we get is instead of that line just going nice and diagonally up, it basically levels off at 20. The next thing that is not perfect about systems is that usually there's some amount of coordination between the parallel workers, or often there is. And that means that they have dependencies on each other. Now, this is not always the case, but it is in lots and lots and lots of systems, that there's some kind of a dependency between these parallel workers. And so if we diagram that, it looks like, hey, I'm doing my little, chunk of blue here, and hold on, I actually need something from the other worker. And this kind of sneaks in a bunch of different ways. It's there can be shared resources or interchange, pairwise interchange of data, various kinds of things happen. And what happens is the task that depends on the other task stops working, so its timeline gets longer. And when it requests something from the other one, it is actually adding work. So more work is appearing here. It's kind of coming out of nowhere. There's the overhead of concurrency itself. And what that does is balloon the total amount of work that the system has to do, which should start to feel familiar because, when your system is unresponsive, sometimes it's just a little bit over the threshold, and it will just basically never come back out of the death spiral. So how bad is this coordination overhead? It's actually pretty bad, and it grows really fast as you grow concurrency. So that's the key point. As you try and increase, you're like, oh, I'm going to really parallelize this, and I'm going to create lots of concurrency. Surprise, the overhead of that just explodes. And so it's basically, at the worst case, it can be as bad as the fully connected graph of all of the workers, which is n times n minus 1 pairs of possible interactions, which is order of n squared. And so remember that n times n minus 1, it goes on the bottom of the equation again with a new parameter called kappa, which is the fraction of work that has to be that is caused by this concurrency overhead, basically what I call crosstalk. And so now our system not only kind of levels off, but it's a little hard to see with the aspect ratio here, but it actually starts to go down. And this is something that you're familiar with, this point of diminishing return. So if you look at benchmarks, you're familiar with seeing benchmarks that kind of climb and then they degrade. You get retrograde scalability. And a point to note about the x-axis on this is that it's in powers of 2. So it's a little bit skewed. The aspect ratio is a little bit skewed. But if you were to plot this with a linear x-axis, you would see that curve kind of rounding off and then going down. So here's a little bit different aspect ratio picture of what happens. And it makes it a little bit more obvious that the blue region, which is the crosstalk penalty, grows really fast and causes this point of diminishing return. So you get this point where if you try and add more work to your system, it actually goes slower and gets less done. All right, so that is that the falling off curve on the bottom is the equation, the graph of the equation of the Universal Scalability Law. So a quick summary of the USL is that, again, it's this function of throughput is a function of concurrency, and it explains why and how systems don't scale linearly. So you can put the equations out of your mind now, and we'll talk about what the USL is good for. So now that we have the USL as sort of a model of how and why systems behave under increasing load or concurrency, we can start to measure and model in those terms. And we can predict when we're kind of getting towards the crest of the hill and we're about to slope off towards the other side. And knowing these things, we can also design better systems. And it's actually pretty easy and fun. And it gets more and more easy as you say, I actually don't need the math. So let's get into measuring, modeling, and predicting. So a really common question, an obvious first question is, well, how do I measure serialization? How do I measure crosstalk? And the answer is, you don't have to. You measure throughput and concurrency. In fact, you really can't measure, or I don't know, I've never been able to. I think it would be really hard to measure these effects directly. But what you do is you measure the symptoms, and then you can infer them from the symptoms. And you do that by collecting the throughput and concurrency data points, and you fit this model with just regression to estimate the parameters. You estimate sigma and kappa. And so what you end up with is a scatter plot, and then you fit the data, you fit the model to the data, and you get the equation, and you draw the equation and see how closely it fits the data points that you collected. So this is a really nice, clean system with very, very good, tightly fitting the model very well kinds of data points that I measured. I'm going to show you another one that's a little bit messier and provide some good things to talk through. So how do we measure these things? Throughput is actually really easy to measure. If you have any kind of monitoring system, you probably have throughput metrics. It's like, page views per second or queries per second or whatever. Almost every system provides this, so it's really easy. Concurrency, there's a couple of different ways to get this. Some systems will provide some kind of a measure of concurrency. So here's a couple of examples. In MySQL, there's a status variable called threads running. There's a status variable from Apache's server status, which is the number of active workers. You get the point. Most systems will have this. Some don't. And for those that don't, what you can do, sorry, I'm getting a little ahead of myself. So what you do is you just poll this variable and get lots of samples of it and average them together over some period of time. And in my experience, it works well to do like 1 minute or 3 minute or 5 minute averages. And what you end up doing is you want to get lots of these. Like you want to get points that have high concurrency and points that have low concurrency. So like if you have a daily pattern of traffic that goes like this, then measure a whole day so that you get the low part and you get the high part. And then divide it into, if it's 5 minute intervals, I think you have 1,440 points. And you want hundreds, you want at least dozens, hundreds. If you were doing this in a clean room in the lab, you could get away with 3 or 5 or 10 points, but in real messy, noisy systems, you want lots of points. You want a cloud of points. So you need to take samples, snapshots of this like once a second, and then average a bunch of them together. If you don't have that metric of concurrency, the other way that you can do this is harking back to what I said earlier. You can measure up latencies, and then you just sum them and group them into time buckets and divide by the length of the time bucket, and you get effectively the same thing. You get average concurrency. And I won't explain how to derive that, but it's just an alternative use of Little's law. And it's pretty easy to diagram and convince yourself that this is the case. So again, get hundreds of data points and make them over ranges of time, because if you look at it in too fine granularity, you just get really, really noisy kind of high frequency data, and you want things that are somewhat smoothed. And you can just plot and look whether you've got super noisy hairballs or whether you're starting to see some patterns in the data. And that is exactly the next step. You literally just do a scatter plot. So put it into Excel and do a scatter plot, or put it into whatever your favorite tool is, Python notebooks or anything, and just do a scatter plot. So this comes from a real system, and I got this by I didn't talk about VividCortex, my company, but what we do is measure every request that enters and leaves a database server, and so this is from a real system where we just measured literally the latency of every single query, and then I just used our APIs to smush that stuff down and average it over time periods, and then I just stuck it into the spreadsheet. So a really high fidelity, very, very accurate way to get this data. All right? And there's one outlying point which makes this data really hard to fit, just because of where that outlying point is, far, far on the edge. And for the purposes of the next few slides, I'm just going to delete that, which is totally legit. So you should feel free to go, I've got 350 points, or I've got 1,440 points, and one of them is just totally borking the model. Delete. This is, trust me, statisticians do this all the time. And then you plug it into an Excel model, and I've linked that here, and at the end I've collected that in the resources slide at the end. So I built this Excel model. You can do this in different ways. I have done it, before I figured out how to model it in Excel, I built a bunch of bash scripts with, GNU plot, and I've done it in R, and I've also done it in Plotly with JavaScript. There's lots and lots of different ways that you can do this, but basically you just plug in the USL equation, and you plug in the data, and you go, do your magic regression, and the regression does its magic, and you end up with the parameters being estimated. And that's, it's really that simple. So the Excel spreadsheet is an easy one. Sometimes Excel is a little tweaky because Excel could only fit things if they're kind of in a certain shape, and so there's some parameters in here that I built in. There's lots of like advanced knobs and stuff that you can tweak in this spreadsheet, but I didn't for this one. This one's data is clean enough that it was just like plug and play and worked fine. So now, now that we've got the line fit through the points and we've got the parameter estimates, what does it mean? So now we have to interpret the output. So a couple of things. One is it shows whether your system has more serialization or crosstalk, and that tells you where your bottleneck is coming from. Should you try and go make things more parallel, or should you try and reduce the cost of parallelism, for example? And you just have to think about your architecture and where these costs are likely coming from. You can see where the curve rolls off and keep yourself away from that. Don't go near that level of concurrency. And you can predict how far in the future that might be if you're not seeing it. So let's look at a couple of examples. One that came to mind was PayPal wrote a blog post about some benchmarks they did benchmarking Java versus Node.js. And the data was super clean and easy to fit. And the parameters on one was like all crosstalk, and the parameters on the other was all serialization. And I'll let you guess which was which. I'll just say Java runs under high concurrency, and Node.js is single-threaded. Right? So if we bring this back to the Rasmussen model of the operating domain, what we're doing here is describing how things happen as you start to encroach into the fuzzy shaded area that you're not really sure about near the bottom there. And what happens there is that the system gets really variable, very unpredictable. And if you just gather this data and then plot it on a spreadsheet, it's super easy to see it happening. You don't need to know the math. You don't need to do anything. You just need to go, ooh, an ideal system would be a straight line, and my hairball is kind of not straight. And you're like, yes, when we get into that region, we're starting to see what's, the system struggling, right? So no modeling necessary. And so let's go back to my data. Again, I've deleted the outlying point here. But when I look at this, I immediately see two things. I see a dark region where there's lots of points, and that is where the system is typically operating. And then I see some outlying regions. And I do kind of two things with this. One is I go, what if I didn't have any outliers? Then I would draw my, I would model and potentially draw out beyond the limits of what I can observe, and I would go, gee, it's starting to level off a little bit. I probably can't count on getting a whole lot more there. And that's on the x-axis. And then I also look at the y-axis, and I look, we're here now, and even if we try and double the amount of load on the system, we kind of only get a little bit further up. So we're starting to see really diminishing returns on investment and returns under load. So again, if you delete the outliers, I already would say don't count on a lot more than what you're seeing from this system right now. And then I kind of draw a box around the outliers and go, this is already the system struggling. This is high concurrency. And what happens when systems get stuck? Things pile up. And what is things piling up? It's high concurrency, which is those points that are far out there. Right? So we can already see that this system, at times, is operating near or maybe even in the degraded mode. So you don't need to model, you don't need to fit, you don't need to look at the parameters. You can just literally plot this and go, that cloud is not pretty at the edge, right? That scatter plot is not pretty at the edge, and there's just meaning in knowing that if it was fitting very nicely and if things were just kind of going up and to the right, you're happy, but when they stop going up and to the right and starts getting messy and the scatter plot gets wider and less consistent, you're not happy. All right? So that's all I've got, and I've got time for questions, and happy to answer them.
So that was super interesting, and when I've worked at places that have had messaging systems, usually the solution we've taken to doing this sort of thinking is looking at queue size, like what the length of the queue is.
Yeah.
And I wonder how that fits into this.
Yeah, so queue length is included in concurrency. So our total concurrency is queue length plus whatever is in process. And your load average, so I didn't really tie this into like our familiar definitions of load, but we talk about load and we think about the load average, and that's actually a queue length. It's the number of tasks that are running and blocked on something, so it's a familiar definition of load. And queue length, or people will call it queue depth, is another expression of, hey, the system is busy, I've got to wait in line. And when the system is busy and I've got to wait in line, then we're asking it for more than it can do right now, and it's basically promising us, I will hold you in line and I'll do that in the future. And when that happens, we start to see, so tying that back to the to the queuing theory model, we start to see really escalating response times because of the length of time that things wait in the queue before they actually get, into process and service.
Hey, this was a really interesting talk. One thing I was curious about was that you applied this to sort of, like requests and the performance in responding to those. Have you done any studies, or do you think it would be applicable also to like the performance of teams of people? And how might we measure throughput and concurrency for teams?
Yeah, I love the way that you're thinking. I actually have another talk on this where I was kind of took this into alternate domains. And one of them is, how people work. And, for example, there's the Amazon rule about how big a team can be in terms of pizzas. And there's, this communication overhead. There's Brooks' law and the mythical man month, talking about how adding people in adds communication and coordination and planning and scheduling overhead and makes something that's late even later, right? So it totally applies. There's also some people have written some blog posts about this. One was, let me think, it's Adrian Collier, I think, was the one who wrote a blog post about applying the USL to teams. So yeah, you're right on there.
Cool, thanks.
Really good talk. I'm familiar with most of that material, but it comes together in a really good way. One thing that was occurring to me as I was listening is that if we are doing load testing, assuming that the system is not otherwise heavily loaded, we actually know the throughput and the concurrency, and we can vary those. So it occurs to me that you could actually build this modeling right into your load testing tool. So you can have it gather the observations that you need, and that actually kind of give you an answer to where the scaling limits of your system would be, and that would be super cool to see.
Yeah, I had a little bit of a hard time hearing the last thing that you said, but can you say that again?
I was just saying that you could actually build, you could modify a load testing tool to actually vary the throughput and concurrency to get the observations that you would need to build the model.
Oh, right.
And
Yeah.
you could actually have your load testing tool just go through that process and spit out the scaling limit.
Yes,
Yeah.
absolutely. Yeah, so you can. So great comment. Thank you. All right, anyone else? Or I'm standing between you and lunch. All right, thank you.